Thank you all for coming. I apologize again for not being able to be there in person, but it's really a great pleasure and satisfaction to be introducing John Kypriotakis for his thesis presentation, his PhD thesis presentation. It's been a long road. I say this because we're not used to instrumentation PhDs at the Institute of Astrophysics here in Crete. But those who know can tell you that instrumentation is a very tricky business, and hopefully you will realize after John's talk why it took so long for this thesis to finish. John has been working mostly in the laboratory of Professor Amaprakas at IUCAA in India, designing and testing the WALOP-North Instrument, one of the two wide field optical polarimeters that will be deployed for the Pacify survey. John has also written all the control software for both instruments, and today he will present a few highlights of all this long trip to Ithaca. John, the floor is yours.
Thank you, Kostas, and thank you all for coming today. I'll try to be as concise as possible because I know everyone wants to go and have some sweets because you've already had lunch, probably. Let's see. Okay, I'll switch using the computer. So the outline of today's presentation is first I will introduce to you why and how we got started on this journey. I will show you the optical design of the instrument we discussed before, its performance. I'll move on, talk a little bit about the mechanics of the instrument, its electronics, and I will conclude with the software, the testing, and the deployment of said software. Now, let me start by introducing you to my journey through this PhD, which started in 2017 when I got introduced to the Pacify project. Pacify aims to make an optical polarimetric map of the galactic poles and the galaxy in general, aiming to do a 3D tomography of the dust within our galaxy. In order to do that, we need to carry out a very highly precise polarimetry for the stars in the regions of interest. And to do that, we need two instruments simultaneously in both hemispheres, one here in Skinnacus and the other in South Africa in SAAO. These instruments would need to perform within very strict requirements, which I will present in this slide. First of all, they need to have a 0.05 polarimetric sensitivity with a 0.1% polarimetric accuracy throughout their entire half a degree by half a degree field of view. And both these requirements are pioneering today since there are instruments that can deliver either or, but not both. They need to be seeing limited, as many instruments constructed today, but they need to fit the very tight space constraints of each of their telescopes. And for Skinnacus, the space constraints are shown here, where you see that, let me show my laser pointer again. So these are the space constraints within the Skinnacus telescope fork. And you see the focal plane, which is about 500 millimeters from the earliest where we can place optics or mechanics, with a total clearance of about a meter, with more or less 1600 millimeters at the widest and 1600 at the widest and 600 at the narrowest. So the space constraints are really small for an instrument of such high field of view and such high precision. So the design choices for the instrument were initially to be a one-shot polarimeter, much like its grandpa, Robopol, And this is one image taken out of RoboPol, and you see that all 4 Stokes parameters for the polarimetry are calculated within one image. So every star has been split in 4. But together with the stars, we have split the sky as well in 4, and then recombined all 4s as a background of each star. So in WALOP, we chose to have 4 fully isolated channels. So both the sky and the starlight are split in 4 distinct channels, and that will reduce background by a quarter and the instrument systematics accordingly. Therefore, we will also have a split pupil instrument, much like RoboPol was, and I'll show you later why a split pupil instrument needs specific optics to operate. The overview of the instrument is shown here. We have a collimator first, immediately after the telescope's mirrors, then a polarizer assembly, which I'll show you later what it's comprised of, and then 4 distinct camera lens arrays, each terminating on a CCD of its own. Let's start with a collimator, and a collimator is essentially an optics array that images each point of its object plane into every point on the image plane. And to help you understand it, I'll have created a schematic here where the collimator lens assembly is represented by a single lens. And you see that this lens takes rays from point A and images them on all points of its image plane, same for point 2 on its object plane and point 3 of its object plane. Why do we need a collimator? Is because exactly we have a split pupil instrument, and therefore we have the need for both prisms to treat the entire field of view equally and not differently. So the light from every point needs to spread and be handled by both prisms. In our case, our collimator is comprised of 6 custom-made lenses, one of which, the third one in the whole array, is a conic lens. And it also needs to fix remaining telescope aberrations. Since our telescope was never meant to operate for half a degree by half a degree field of view, some aberrations do exist, and we need to also fix them, and we do that through our collimator. Also, finally, it uses pre-optics to conserve space. So we do not put optics only after the focal plane, but also before the focal plane. That's because we have tight space constraints and we couldn't afford to lose any amount of space. Next, I will talk about the polarizer assembly of WALOP, which has 2 calcite Wollaston prisms. And we had to choose calcite because its competition, quartz, would not split the ordinary and extraordinary, the 2 polarizations, enough for half a degree by half a degree field of view to be manageable. So we had to go with calcite, which is more expensive. It's only naturally made. We cannot artificially make calcite for the prisms. It has its drawbacks, but it was our only design choice at the moment. We had to also go with a very large prism. So it's a 75 by 50 by 46 millimeter prisms, and they are about this big, if you want a size comparison. Here are the schematics. You can see the 2 side views, the top view and the isometric view of the prisms. And as you see, they are quite big and cemented together, the 2 halflets of the Wollaston in the middle diagonally, as the Wollaston prescription goes. Now, each prism is preceded by a 75 by 50 millimeter rectangular half wave plate placed at the interface between the prisms and the glass wedge made out of BK7. The half wave plate goes out here, and these glass wedges are preceding the prisms in such a way that the 2 rays are diverted away from the 2 prism interface that I'm showing right now with a laser here. Now, the prisms would split the field normally, but we needed the 4 channels to be diverted 90 degrees away of each other. And that's why we follow up the prism array shown here by 2 polarizing beam splitters and 2 mirrors, 2 and 2 on each of the beams, in order to be able to fully spread the field into 90-degree angles. The next problem that we faced, due to using prisms such big and with such big split angle, is that Wollaston prisms have a wavelength dependent behavior. That means that the split angle that they provide to polarization depends on the wavelength, and for light that is not monochromatic, that means that we get elongated PSFs towards one axis, the split axis of the Wollaston prisms. So the images that should look like this would look like that, with PSFs elongated and elliptical. How we solved this issue is we drew inspiration from the atmospheric dispersion correctors used to fix light coming from the atmosphere, and we converted them into what we called Wollaston dispersion correctors. And they look a little bit like this. There are two glass wedges that are stuck together using an optical cement, and that fixed this behavior and gave us the original nice images that we aim to get. In order to further minimize cost, we decided to make them similar in pairs. So we need 4, 1 for each of the channels. We made them by 2 similar to reduce the cost extra. We then go to the camera optics, and as I told you before, the light will emerge from the prisms unfocused, having gone through a collimator first. So we need 4 camera assemblies, 1 for each channel, to be able to focus the images back into a CCD, 1 for each. And as you see, this is the entire optical design with the collimator that I mentioned before, the Wollaston prisms placed here, the polarizing beam splitters underneath, and then the camera assemblies take on 1 for each channel. You see them color-coded here with blue, cyan, magenta, and orange. They all terminate into 1 CCD, focusing the light. In pairs, they are identical. So the lenses in the camera assembly 1 terminating in CCD1 are the same as in 2, and 3 and 4 are also similar in pairs. So we reduce cost even further. 6 lenses in every camera assembly, one of them being conic, the last lens before the CCD. We also placed extra mirrors. You can see them here and here for CCD assemblies 1 and 3. And that reduces further the x-axis of our instrument size. We then move on to our filters. Initially, in Pacify, we had discussed using Johnson's R filters, which turn out to produce better signal-to-noise ratio in photometry, but worse PSFs in our image. And to explain why, I've given you these 2 spectra here. On the x-axis of both graphs, you see the wavelength in angstroms, and on y, with blue, is a typical sky spectrum at Skinnacus. With red, the filter transmittances for SDSSR on top and Johnson's R on the bottom, and with green, the convolved transmittance with a spectrum. And as you see, Johnson's R, shown below, has a much wider profile, extending up to many, many wavelengths outside the SDSSR filter. That's why it's able to provide better SNR but worse PSF, because our optics cannot handle this wide array of wavelengths. One solution was to use indeed the SDSSR filter shown here, which did provide us with a better PSF, but a marginally worse signal-to-noise ratio, which we are able to counter with a little bit more, with a better PSF, because we will actually be able to make better photometry. But as it turns out, as the SDSSR filters introduce polarization because they're not just colored glasses. And you see here that on the x-axis, we have the initial polarization of a star, and on the y-axis, we have the introduced polarization by the filter for different angles of incidence of 0, 5, and 10 degrees. And I remind you, these are collimated angles of incidence and not real angles in the sky. And you see for unpolarized stars, which are the focus of Pacify, the introduced polarization goes up to 0.6% or more in the angles of incidence that we expect in the instrument. Our choice was to design, together with Asahi, we did the polarimetric modeling, a new non-polarizing SDSSR filter by tuning the dielectrics in such a way that the polarization introduced was minimal. And you see that indeed, for the same angles of incidence, we get a maximum of a little bit above 0.08% polarization, which is within the limits acceptable by Pacify, especially after calibration, which I will show later. Now, the guider of such an instrument also needed to be redesigned, and that's because we needed to replace the entire gum underneath the telescope, and with it, the existing guiders at both telescopes. We also need to be able to handle huge aberrations, because we need to be collecting light outside the 0.5 degree by 0.5 degree field of view. We need to have a limited size for the guider itself, because it does add to the size of the instrument. And we also need to deal with very few stars in the regions of interest of Pacify. We make the choice of having a rotating guider versus a patrolling one, which means that we have a guider with a very narrow field of view that can rotate around the entire scientific field of view and maximize its effective guiding area without needing a large instantaneous guiding area. And you can see such designs here. This is a patrolling guider, and this is a rotating guider, where in the case of WALOP-North, the guider rotates 360 degrees around the field of view and not truncated to the 90 degrees I'm showing here. Our guider is using two lenses and 3 mirrors. The 3 mirrors are there to conserve space, and the 2 lenses are there to undo aberrations by the telescope. And they're also using achromatic CCDs, which I've marked black because it's something that has been used before in astronomy. Since we do not care about color when guiding, we can use the entire spectral range and maximize our throughput. Now let's discuss the performance of an instrument because, well, I've shown you one design that works, but does it work? Well, it introduces no significant vignetting above the vignetting of the telescope itself. It is indeed seeing limited. It has pixel perfect alignment, and both those two effects can be shown here, since these are the PSFs expected by WALOP-North, convolved with the PSF that we measure at Skinnacus for all 4 detectors. You see the 4 curves aligned within 1 pixel of our CCD. The blue here corresponds to pixels, the red one corresponds to arc seconds on an arbitrary axis within the instrument. And you see that all curves fall within 1 pixel, and they are indeed seeing limited. So the width of the curves is dominated by the 1.1 arc second seeing we would expect normally at Skinnacus. The spots of the instrument are also symmetrical, and you can see it here. You have the 4 detectors, 1, 2, 3, and 4 of WALOP-North. The spots have all RMS within the pixel size, RMS radius, and geometric radius within the Nyquist limit of 2.5 pixels of WALOP-North. So for different fields of view, this is true for all fields of view and all detectors. Moving on to calibration, as you can tell by the complexity of the instrument, we cannot just fit a Mueller matrix to the instrument and be done with its calibration this way. We had to go above it, and we had to fit the retrieved, the real Q and U here to the observed Q and U, shown with Q naught, U naught, with second order polynomials. So we have the steady terms, A naught and B naught, which is essentially the instrument offset. We have AQ, AU, BQ, and BU, the linear terms corresponding to the Mueller matrices that we would normally use. And then we have these 3 higher order terms in each equation, which are proportional to Q and U squared, and the mixed QU term, which is there for a very particular reason that I will show you later, namely covariance. In order to be able to fit this, we had to also overcome some limitations by Zemax, namely the fact that Zemax can only handle fully polarized light and not partially polarized light, and it can also fit 12 field points at a time and provide us with essentially 0 accuracy over the entire field. So we created a model where, with using the Zemax programming language, we were able to get measurements for 144 points within our field and within 45 points on the Poincare sphere and at the center of it. So unpolarized and fully polarized light only. We were able to infer these parameters by interpolating over those. I should also mention this is a noised model, so we did add photon noise on top, which Zemax usually ignores. Now let's move on to the calibration performance, starting with the covariance matrix shown here. So on the diagonal is the QQ and UU covariance, and on the secondary diagonal we have the QU and UQ covariance. As low as possible is the target, and you see that we have an absolute covariance within QQ and UU, and the negligible covariance in the secondary diagonal, which is what we were actually aiming for. And that gets solved by using the mixed term. These plots looked much worse without the mixed term handled by our model. We then move on to the standard deviation of the calibrated minus the theoretical minus calibrated retrieved parameters. And let me remind you, this is a noised model. You see in the left, we are, in the left and in the right, we are very, very low in the standard deviation that we get. So we have a model that does actually perform well, does not have huge tails. You see only one small arc that performs worse, and I will explain this arc in the very next slide, where I'll be showing you the translation plots for the instrument. So on the top, you have images of the retrieved Q, calibrated Q, for input QU of 1 nil, and retrieved U for input of 1 nil, and on the bottom, Q and U for inputs of nil 1 accordingly. The primary diagonal here is the throughput of the instrument, essentially how well we retrieve the parameters, and the secondary diagonal is the crosstalk, essentially how much Q or U is converted to U and Q accordingly. And you see again that we have only one problematic region in this arc, and essentially that region corresponds to a position of crosstalk between the two prisms, and that's caused by the interface between the half waveplanes. And this is increasing the crosstalk, but this is only a very small area. It looks bigger here, and that's because of our sampling. So essentially, it's 1 pixel wide, but this is the pixel size that is as thick as that, and that's why the effect gets exaggerated in the plots. We will now move on to tolerancing. So we have created an instrument and we have created a calibration strategy that we can simulate on sky using half wave plates and polarizers. We might as well see whether this is a realizable design, whether the design holds in real life. And we had to take care of manufacturing tolerances. So as you see here, this is a very complex instrument. It uses a lot of lenses, a lot of prisms and other optics. And these all come with manufacturing imperfections, and we have to simulate them. We also have to simulate assembly tolerances. So not every hand is perfect, and the lenses will not be glued and aligned perfectly. We need to take that into account as well. We also have to take into account environmental tolerances. So the lenses bend and get deformed due to environmental differences in temperature, pressure, etc. So we have to also take that into account. So within reasonable limits of these three, we ran a Monte Carlo simulation of 10 to the 9 systems within ZMEX, and using only back focus compensation, which means that the CCD is placed here, 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 and somewhere here, we were able to get an RMS max of 40 micrometers. So the RMS would fall within more or less 2.5 pixels, which is what we were interested in initially. The motors that will be able to sustain such an instrument is one facilitator of the in-out movement of the calibration half-wave plate, one rotator of this said half-wave plate, a facilitator of the in-out movement of the calibration polarizer, one rotator of such polarizer, and the design of this one is shown here, where we have the motor coupled over a helical never-ending spiral to a hollow helical gear shown here. And within this gear, we have placed our calibration polarizer. We also have a motor to move the filter wheel to change our filters. And for CCD focusing motors to focus the CCDs, as mentioned before, using their back focus. And one guider motor that will rotate the entire guider around the field of view. All these motors need to be controlled somehow, and that's why we need precise electronics and software, which I will present later. Let's go on to these electronics. Our electronics needed to be modular, so that means that they are every component is isolated and it can be upgraded on its own. They need to be upgradable, so we need to be able to remove components and replace them as needed, and they need to be independent. So if one component breaks or fries, we can replace it without losing our instrument meanwhile. And we start with power supplies and CCDs to motion control cards, CCD controllers, and thermoelectrics. And I will analyze each of them in some detail. Starting with power. So we have triply redundant fail-safe power supplies, and it should soon be apparent why we need that. They are all heat surge, EMI, and RFI protected, and that's especially the EMI and RFI part is because at Skinnacus, it's not unheard of to have lots of lightning, and that can easily burn power supplies. And finally, they need to have alarms and telematics so we know if anything goes wrong and when it goes wrong so that we can intervene meanwhile. Let's go on to our CCDs, which are actually deep depletion device, not charged couple. They are housed in dewars, which will keep them cool and under vacuum for protection. They have very high quantum efficiency. Ours are procured by a company called E2V, and you can see the quantum efficiency plots here that within the optical range of 500 to 800 nanometers, more or less, we have a quantum efficiency of around 90% for our CCDs. And they have a very low readout noise with its plot shown here. Our readout speeds would be on the order of 100K, so our read noises are around 2.5 electrons. These CCDs will be read using ITSAC cards, which are manufactured in IUCA. So we have the privilege of having characterization in-house and having them produced in-house so we can change them whenever needed. They are very low noise, they are high speed, they are able to perform in the readout speeds that I mentioned before. They are 4 channels, meaning they read the CCD from all 4 corners simultaneously, and that will give us time advantages, essentially sub-quadrupling the time needed to read the CCDs. 16 bits, which are up to par with current astronomical standards, and they use FPGAs, actually custom Virtex 5 FPGAs. So we have a full knowledge of their software at all times. And you can see one of those ITSAC cards being characterized in the lab here. Now, the reason that we actually need the triply fail-safe power supplies are thermoelectrics. Our CCDs are cooled to minus 100 degrees during operation, and that's standard pretty much in all astronomy to have CCDs cooled that low to reduce the dark current. But our large calcite prisms will break even under the very small thermal stresses of being heated and cooled at all times. So we had to take a measure to keep them cool at all times. So our Wollaston prisms are cooled 24/7 all year round in order to avoid them breaking. And that's an extra reason that we need redundant power supplies and triply fail-safe them, is that if all power gets lost in the instrument, we essentially lose the entire instrument. Another feat is that it's impossible to non-destructively stop their cooling. You have to go and physically yank the cables out of the thermoelectric coolers if you want them to stop operating for the Wollaston prisms. And that's again because that's actually what's keeping the instrument alive at this point. Let's move on now to how we control the motion of the instrument. All the motors need to be controlled cost effectively, and that's both in power and in optics. We need to not have any optical parts within the motor control, such as light switches. To do that, we have what we call motion control cards, which are comprised of one card called the green card and 4 white dwarfs on each card. And this is shown here where you see the green card and the 4 white dwarf cards on it. And this setup splits the job between these 2 cards. The green card will be doing input-output, internet monitoring, and command handling by the user, while the white dwarfs will each be handling one stepper motor's clock. They are swappable in case something goes wrong, and they're fully agnostic of both the green card they're operating on and the motor they're operating for. And this is again to reduce any kind of downtime for our instrument. We can move on to the last thing that we control, and that is the telescopes. You can see them here. On the left is the Skinnacus 1.3 meter telescope, and on the right is the 1 meter Elizabeth telescope in South Africa. And we need to have the software flexibility to be able to handle differences, such as the difference in the 2 telescopes. For example, guiding. The Skinnacus telescope does not do guiding internally, while the South African telescope's TCS does the guiding for us. We need to be able to handle differences between the instrument. For example, the Northern instrument, being more compact, has a different guider, which uses only 1 motor to rotate it. The Southern instrument uses 2 motors to pivot it around the field. So the software needs to take that into account as well. and we also need to handle differences between the weather station of the two observatories. So we need a modular software. We need to not be reinventing the wheel every time we're going from north to south. So we just change the configuration and everything should work. To do that, in the end, we have a full software ecosystem for Pacify. It's taking care of everything from planning the survey to collecting the data and finally analyzing them. It provides a human-computer interface for humans to be able to interact with it and change the survey strategy as necessary or assume full control of the instrument if it's needed. And finally, it needs to work out the complex parts of WALOP and command it accordingly. And for that, we have a full ecosystem, starting with the observation planner written in Python by Dima and Sebastian. It's providing a nightly schedule to the user who uploads it to the control software of our instrument and telescope. It will take care of collecting science and calibration data robotically from the telescope and feeding them to the WALOP analysis pipeline, also developed by Dima, which will feed the polarimetry back to the user to be handled by the Pacify collaboration. This slide just serves as a reminder of what the control software needs to control. So a telescope, many distinct motors for the calibration, filter wheel, and guider. The guider camera itself, 4 CCDs, and the weather station. And it needs to report all of that back to the user and to its own database. In the heart of this control software lies the backend, which will control this complex instrument and will authenticate the users. And this is very important because we need to be able to work no matter what fails within the instrument, and we need to be able to work online. So user authentication is paramount. It also needs to log everything that happens within the instrument and the observatory, and it needs to always assure the quality of the output images no matter what. So we chose to use state-of-the-art frameworks to develop this backend, starting with Node.js, working with Express.js, WebSockets, Redis, which actually handles the entire state of the instrument in memory instead of in disk, or in parallel with the disk to provide lightning speed control of the instrument. Handlebars to dress the responses to the user accordingly, and it provides Discord notification to the admins so that we can troubleshoot the instrument at all times. All these frameworks have never been used together in astronomy before, so we had to make beyond state-of-the-art protocols to make them work together and work towards our causes. Astronomers are really well known to work in Python and only in Python, so we had to push beyond to have JavaScript work with what we want to do. The WALOP camera software is a dedicated software that will control all 4 CCDs simultaneously. So the problem is we have 4 CCDs and they need to start and end exposure at exactly the same time. And we cannot limit ourselves to the communication to the CCDs to have that happen. So we need few microseconds of accuracy, and we need to also reduce the overhead. So while the CCDs are exposing or while the CCDs are saving the images, reading the CCDs, we need to be able to be doing other things with our telescope, slowing, for example. For that, we have created a dedicated C software that clock times these ITSAC cards within 15 microseconds proven. And it resides within the instrument itself. So this WALOP camera software lives within the instrument to be able to time the CCDs so well, and it provides 0 overhead. So it's completely independent to the motion of the instrument or the telescope. And you can see one example image that we were able to retrieve within 15 microseconds of accuracy. So you can do the calculation of saving a 130 megabyte image within 15 microseconds. That's why we had to use C instead of any other language available out there. Finally, on the side of WALOP control, we have the front end, which provides a modern UI. You can see here the control of the calibration half-wave plate and polarizer. Everything is scalable. We can add extra components if necessary. Everything is responsive, so the user has a live image of the instrument at all times within their browser. And it uses, again, state-of-the-art frameworks like React.js and Redux.js along with Material UI, which at the moment lives at every single phone out there to provide us with a user interface that we see in our iPhones and Androids right now. Finally, it's able to work robotically, so the user can just upload the schedule and have the front end observed for them, and they can just monitor the state as a fail-safe. Our database needs to be accessible 24/7, and it needs to have production standards. It needs to be normalizable. It needs to be written and read to as fast as possible, and it needs to have many relational properties. For that, we chose the Atlas Cloud's MongoDB, which is it's hosted on the cloud with multiple fail-safes so that it never gets lost, and it's as fast as it can be since it's being used by Facebook right now. So that's how I know it's fast enough. You can see one snapshot of our database here, and you can see the complex relations between schedules, filter wheel states, calibration states, observations, etc. In the end, we need this software to be continuously integrated and deployed to our servers. So we need zero downtime every time we push code, and we need updates deployed to the server as fast as possible. To do that, we have an automated pipeline hosted in our own Git repository. It's a copycat of GitHub. It takes care of automatically testing, packaging, and deploying the software with as low as 30 seconds of downtime whenever a new update is pushed, and with 15 minutes release times. So from the moment a developer pushes code to the moment this code is active on the server, it takes about 15 minutes. The testing mentioned before is automated and on every update, and it's handled automatically by our pipeline. When it gets results different than the ones it expects, it halts deployment of the code and awaits for the approval of a developer. We have specialized testing frameworks for our own code base and optimized for our own code base so that our tests run as fast as possible. And we have unit and integration tests automatically through the CI/CD pipeline I explained before, but our end-to-end tests happen hands-on using specialized protocols requiring one lead developer, probably me, and one lead engineer, probably someone in IUCA, who both use a configuration of the code specialized for developers so we can see extra data than the average user. And we test all components live in real hardware, unlike the unit and integration tests mentioned before, which happen on simulated hardware. You can see one such test here that we did the other day in IUCA. It's going to be testing the guider for WALOP South, which I remind you uses 2 motors. So the command has been given. You see the motors, the real hardware motors slowly slewing. And in the end, the user gets the response that everything is done, and you'll see the guider position that has been marked as moved. Concluding, I would like to tell you that we have made 2 of-a-kind instruments, since we have one in the north and one in the south. They are state-of-the-art from the bone to the skin, from their optics to the software, which has been customly made in-house and is upgradable. It can operate robotically and collect the data for us. All we need to do is provide it with a schedule for these operations, and it has 0 overhead from the database to the front end. It writes as fast and it reads as fast as it can. Closing, I would like to thank my supervisor. I would like to thank Ram, whose facilities I've used for so long. Vasilis, whom I dare say is a personal friend at this point. Steve Williams in United States Naval Observatory, who has been helping me every step of the way, psychologically or even by proofreading my material from every now and then. My PhD committee, who have convened to watch me present, the personnel of our Institute of Astrophysics, and the personnel of the IUCA Instrumentation Lab. And the meme on the side is for everyone who wants to join instrumentation. They should expect problems every step of the way. So thank you all.
Thank you, John. Okay, questions from the audience first. Can you please, Vaso, can you please handle this?
Questions from the audience. Pablo?
Yes, such a complex system, so many components. What is expected with instrumental polarization? How it's going to affect that precision we want to get?
So that, let me show you the appropriate slide. I'll take you all the way back to calibration.
I'm sorry. I know you can hear me very loudly. Can you repeat the question, because we cannot hear the questions of the guys who are online?
Yes, sorry. So the question was from Pablo Rick from our Institute of Astrophysics, and he asked that for such a highly complex instrument, how can we expect and how low can we expect the retrieved polarization instrumental systematics to be? That's why I have now shifted back in the standard deviation of the difference between the input and calibrated Q and U standard deviations. And as you see, they are all beyond the 0.02% in the calibrated data for almost the entire field of view, except the small arc of high crosstalk between the 4 channels. It's essentially the calibration that saves us from all the systematics, which, for example, I also presented before, the filter that does introduce some of the systematics that we are calibrating here. On Sky, this will happen with the dedicated calibration half-wave plate and polarizer.
Other questions? Yeah.
So that means that someone can set with that. You will have someone mounted opening telescope around the base of the open.
I'll relay your question first and I'll answer it. So it was Ioannis Kypriotakis from Institute of Astrophysics who asked whether the software will be accessible outside the observatory facilities and whether there can be someone from their office controlling the instrument and telescope and having them observe for them. The answer is that yes, they can, but no, they shouldn't. So it will be accessible anywhere. You can just VPN into the physics department and you can boot the webpage and control everything. But for safety measures only, at least 2 people will be at the observatory ready to close down if anything happens. Because, well, something might happen. The lines might break from here to the observatory if they are physical lines, or the line of sight might be cut for some reason and have no internet connection up there. So someone needs to be there to close down if necessary.
Questions? Other questions? Anyone?
Nice presentation. I have 2 questions actually. The first one has to do with the cameras. How sensitive or critical is the calibration of each camera? I mean, is it possible to have as much as the same sensitivity as possible, or it's okay if they have different calibration?
So it was Grigoris Maravellas from the Observatory of Athens. Really? How? Okay. And the question was whether the cross-camera sensitivity differences will play any role in the instrument systematics. The proper answer to it is that we are taking care of it within the calibration, because the calibration will happen with the real hardware that we're using, and it's going to be happening on Sky. Differences in the sensitivity between the 4 CCDs will be taken care of the model, the calibration model itself. So they will be calibrated out. In general, we need them to be as sensitive as possible and as uniform as possible between each other and within themselves, but it shouldn't matter much because the calibration will be cross-camera and cross-field. And the second one?
So what is it, which task took the difficulty from time, but you spend the less time?
That's a good question. Well, calibration took 3 or 4 slides, but it took some time. I think it would be the optical design because we stumbled upon many unknowns there. We stumbled upon prisms breaking, which you cannot control it. We stumbled upon this wavelength dependent behavior, which we only guessed but didn't know. and we had to fix them in real time, while other stuff like software hiccups that might have existed or electronics hiccups either were already solved by someone, or at least something else was going underway, like the assembly of the instruments while we were working on those. So I'm going to have to say the optical part, either design or assembly. Thank you.
Questions from not the committee?
No, just general. I think I know if everybody here knows, but I'm just to ask the very basic questions. You have two instruments. What's the status of these instruments and when are they going to be installed?
Right now?
Yeah.
Okay, the question was from Mr. Professor Papazoglou, who is a professor in the material science department, right? Because I had an error before with the affiliation. And the question was, what's the current status of both instruments? Both instruments are right now in the assembly phase. So the southern instrument is finishing assembly and the northern instrument is starting assembly right now. Most of the components are here for both of them. For the south, all of them are here. They're not here, and they're being assembled. Vangelis.
Is there maintenance instrument? How long do you expect it to perform?
That's a tough question. The question was from Vangelis Padoulas, who is a technician in our Institute of Astrophysics and the Skinnacus Observatory. And the question was, what's the expected maintenance time and the expected lifetime of the instruments, I guess. The expected lifetime is, it's very tough to say. I hope they last more than 10 years. That's what I'll say. And the maintenance time is, I think we would need some frequent maintenance in the beginning, but then I think we should be able to iron out all the details and have them work for their lifetime with minimal maintenance. The cooling phase. Okay. Okay, so the question is from Anna Sinani from our Institute of Astrophysics. The question was, what if the cooling fails? And I'll take you to the slide of cooling just because I created that meme myself, no other reason. Well, if the cooling fails, the instrument needs to go back to IUCAA, be disassembled, the broken prisms be sent back to Karl Lambrecht in the US, re-cemented, brought back, and that would mean at least a year of downtime. But we hope it never happens. And that's because we have them in redundant power. So 3 power supplies. If one of them fails, we get the first alarm and we get to replace it. If another one fails, we get another alarm and we get to replace that one as well. For all 3 of them to be broken, and someone must have made it on purpose if all of them break. It's not going to be me, but it's going to be someone. And at least 2 of those redundant powers are off the grid. So it's not like we're going to have a spike from the grid that will fry them. I don't know if I answered the question. The question is, it's not going to happen. The answer is, it's not going to happen. Yeah. Thanks.
Anything else? Goes once, goes twice.
Stoned.
We're going to thank John again.
Thank you.
Okay. And then I would kindly ask everyone on Zoom and physically in the room to leave so that we can start the examination process.